Questions? Yeah.
Did I understand the example of the base possible from the base?
Yes. You mean how I got that
Yes,
relation?
yeah.
Sure, let's go with that. I'm taking the following convention. Here is the arc of knot. Here's the base point, and here's a loop that is going around the knot, around the arc of the knot and coming back to the base. So if I'm going to give them the same label, A, all right? So that's a little schizophrenic, but you see what I mean. I'm going to label a loop that goes around the arc by the same name as the arc, okay? And then we can see some things. For example, we can see the following, that if we had two arcs in the diagram next to one another like that, and we drew a curve that went around both of them, then I claim, and let's say this one was B and this one was A, then I claim that this is homotopic to BA. First do B and then do A. And we're just going to draw a picture of that, right? So let me draw another version. So here are my two arcs. And now I want to draw first B. So that's right. Now the base point is, think of the base point as out here, all right? Up above the plane. So then to do B, I would come down here and come back up, and I go over it. So I would do B by coming around and coming back here and up over A. And now let me leave a little space. And let me put that crossing in correctly. Over. And this one is also over. So far this is B. So I'm coming down, I'm going around this and I'm coming back up. And I'm ignoring A because I'm up here above the plane and I'm coming down to that arc and coming back up to that arc. Okay. Now I'm going to do A. So here I am at the base point and I go around A and I come back. Now I put myself at the base point. So we need to fix that here over. So starting here, I'm doing A. So you see I'm doing B and then I'm doing A. And I left a little space at the base point because that's okay, right? If I'm going to multiply two loops, I don't have to go all the way back to the base point. I can just go right near the base point and then start up again. So there I am. But now you see that this is deforming over to this. Just take this part here and slide it this way, and it goes all the way around the back. Right? Reidemeister 2 move, in other words. On the loop. Is that clear? Or not?
Yes.
Yeah, okay. So that tells us that if we encircle two parallel arcs, then the corresponding element in the fundamental group of the complement is the product of those two. Where it's the product of the ones on for the individual arcs. And then I'm making use of that to see a relation that will occur at a crossing, because if I have a crossing here like this, why then I'm not going to change color. I can have a loop that goes around both of them down here. And let's suppose for our purposes, that this one is now labeled A, and this is the one that's labeled B. That's the way I labeled it before, and this is labeled C. Okay, so then, if I take this loop and I slide it all the way up, I will have it encircling these two. If I keep it down here, it encircles these two. So what I get is that this implies that A times B is equal to B times C. And that means that I get that relationship for the loops at a crossing in the knot diagram, and that says that C is equal to B inverse AB. And so that means that if I'm looking at some specific knot, like, for example, the trefoil knot, then if I were to define A star B to be equal to B inverse AB, then if I had here A and B and C, then I get three equations. I get that D is equal to A star C. I get C is equal to B star C, B star A. A is equal to C star B. And of course, I can write those out group theoretically. So I can define G of the knot diagram to be equal to, in this case, A is generated by A and B and C. And we have the relations B is equal to C inverse AC, and C is equal to A inverse BA, and A is equal to B inverse BB. This is our group by generators and relations. And we had some loose ends to talk about with regard to that as well. There are a number of loose ends, some of which I won't try to do, but I will give you a reference, and it'll be in the Google list of things. The theorem is that the fundamental group I1 of the free space minus the knot is given by these generators and relations. By these, of course, I mean this relation, this conjugacy relation, C equals B inverse AB, written down one relation at each crossing and generated by the arcs in the diagram. Well, just like I did here, but that really is the fundamental group. The fundamental group is defined as loops based at the base point, modulo homotopy, and so there's something to be done there. And there are some theorems about how you can amalgamate and figure out what a homotopy group is. And there are some references about that. A couple of references that I recommend for learning about this kind of thing, if you happen to want to look at it, and I still look at these books myself, is there's a book by Massey called Introduction to Algebraic Topology. That's one reference. And another reference is Stillwell. combinatorial group theory and topology. Oh my God. But I'm saying it out loud, so I hope you can read it. Combinatorial group theory and topology by Stillwell, and Introduction to Algebraic Topology by Massey. And of course, there are many, many books about this subject, but those are good ones. It's good to hold in your mind how this works, because this shows you how it is that the fundamental group acquires this relation. And the thing is that we can, if we want to, tying up loose ends, we can, if we want to, just define a group this way, right? As though we were never heard of the fundamental group. We just define it to be generated by the arcs with one relation at each crossing, just like that. And then you can see what happens under Rademacher moves to this group. But we already saw that, because we checked that how these behave under the quandle moves. And we saw that this is a quandle, and that meant that it was going to not change under Rademacher moves. And so if you think about what that says about this group, it says this group undergoes an isomorphism if you do a Rademacher move. So this group is an invariant under Rademacher moves. So we know by a little exercising that G of K, that is this group given by generators and relations, is invariant under Rademacher moves. So if that's all we wanted to know, that would be fine. Now we know it's an invariant of the knot. The group is an invariant of the knot. But what you would like to know is that this geometric definition works, and for that I refer you to thinking about it outside this course of lectures. And it's very good to be able to know that, because what that means is that sometimes with a knot that you're working with, or a space that you're working with, you can use the fact that this is given topologically to find a different presentation of the group that's easier than the one you would get from the diagram. So you have more flexibility if you can work topologically. You can't always work topologically. Sometimes things are only defined combinatorially, but if you can work topologically, that's good. So I wanted to play with this group just a little bit more. So now, if we want to play with this group to understand it a little better, one of the things that we can do is say, well, let's see. C is given in terms of A and B. So I could put in for C the definitions of A and B, but I have to be careful, because it's easier with the diagram to show you what I'm thinking, all right? Let's take the diagram. Now let's suppose that we happen to like A and B. Then we can say, all right, then this is B inverse AB. And then we can say, but if I take B inverse AB, and this is C, and and what is C? I'm sorry, I'm being, that's B inverse AB. And what about C? C here, which is what, this was B, no, I'm sorry. I'm being inarticulate here, so let's leave that way, right? I just want to use A and B, although that's what it was. I wanted to use the same letters that I had before. And if I'm going to use the same letters that I had before, then what's coming into B? A is indeed B. All right, that's what we have called B. And this one was called C. But I won't call it C. I just want to use the letters A and B if I can. So then this guy here is equal to A inverse BA. Right, A star, B star A, B star A, right there, right? And then I get another relationship here. I'm getting that A star B, A star A inverse BA will be equal to B, and I'm also getting that this starred with B will be equal to A. So I'm getting a couple of things. One of them is that B should be equal to A times A inverse BA, because I come through there, and I'm getting from here that A is equal to A inverse BA times B. And this would be the same as, but I'm being clumsy about it over here, of letting go of the C and letting go of some things and substituting other things for them, so that I only use two letters out of the three. Okay, so I'm just doing algebraic substitution. But for the sake of showing it to you, I think it's better to do it this way, or I just didn't have a label for that edge. So I'm only using A and B. So that means that the group is actually generated by A and B with these two relations. But what are they? Let's write them out. This is B inverse A inverse B A B. And this one is A inverse B A inverse A inverse B A. Alas, it's complicated, but it's not so complicated. A inverse B inverse A inverse, yeah, A inverse B A. I hope. No, I've got it right there. This, writing this backwards, I got A inverse B A, right? A inverse B inverse A. A inverse B A. Then these canceled. So this becomes A inverse B inverse A B A. All right. So now I'm just doing algebra here, and hopefully I'm not going to make a mistake in my algebra. So one relation is now reading, this relation is now reading B is equal to A inverse B inverse ABA, which could be rewritten by multiplying by A and then multiplying by B, and I get BAB equals ABA. So that's the same as this. Now what about this one? This one says A equals B inverse A inverse BAB. And that's the same multiplying by B and by A as ABA equals BAB. So you see my algebra tells me that these are the same, and it tells me that the group of the trefoil knot is isomorphic to what's generated by just A and B, with ABA equal to BAB. And that's memorable, right? Nice, elegant relation for the trefoil knot group. And you didn't need C. C is given in terms of A and B. Happens to be. C is A inverse BA. You didn't need C. So then you're faced with this group, and you would like to know that this is a non-trivial group. You'd like to know that it's a non-commutative group. You'd like to know that it is infinite, in fact, because it is. It is infinite. It's not a finite group. So how are you going to find out some of those things? Well, that's where the other exercise that I gave you last time comes in. So now I can leave this board. We can remember this easily enough and bring it back up. But that's the fundamental group that they're found on. So let's go on. Another group that I was telling you about, H, is the group which is generated by R and S, such that RSR equals SRS, and R squared equals S squared equals the identity element of the group. Now I'm claiming, I don't know if I wrote it down that way last time, I think I did, but my claim about that group is that this is finite, and that it's actually isomorphic to S3, the group of permutation of three objects. Now, the interesting thing about doing an exercise like this is you can do it and refamiliarize yourself with the definition of a group that's given by generators and relations. So let's think about that. Suppose that I had some word like R, S, R, S, R. If I put in any power, it'll be the identity. So words that I can write are things like this, or SRS, R, things like that. Those are typical words in this group, right? And remember, the definition of this group is that I write all possible words involving the generators. And in this case, very simple, that a word is just a letter appearing or not. Any higher powers are gone, right? So you're just going to have alternating letters. If I had something like this, R squared S, well, that's just equal to S because R squared is the identity. But what about a word like this? If you have an alternation, RSR, why then it can be replaced by SRS, and then you have SR, but S squared is the identity, so I get SR and R, and then I just get S. So you see the words are all falling apart, they're all collapsing, this one, SRS, is RSR, R, and R squared is equal to the identity, so I just get RS. But RS doesn't collapse. So what are the residue words after using the equivalence relation? What can you make? Well, you have the identity. You have R, you have S, you have RS, you have SR. 1, 2, 3, 4, 5. What am I missing? RSR. Right? But any longer word, if you started a word RS and you put an R in it, it will collapse. RSR is SRS. Unless it was just 3. RSR, of course, is equal to SRS. SR, and then you put an S there, it'll turn into RSR. So there are 6 elements. This is it. These are all the possible reduced words in the group. That's all there is. And if you're not convinced from my speaking, stare at it yourself until you really are convinced. But you see, sometimes you have a presented group and you just start looking for the residue words and you find out you have a finite group. And that's great. If you have a finite group, you can really begin to think about it directly. Now, what about the products? Well, you see, you can make a multiplication table. R times S is RS. So about, let's try something. RS times SR. RS times SR is equal to the identity. So these two are inverses of one another. what if you multiplied RSR by R, you'd get SR. And if you multiplied it by S times RSR, well, that's equal to SRS times R. And now you're confronting the fact that it's given to be associative, right? By definition, it's associative because you're looking at all words taken as associated products because you're making a group. The axioms for a group say it's associative. You can, of course, do other kinds of universal algebra if you ever get involved in it. And you might, if you were thinking about quantiles, where you wouldn't assume it's associative. But here it's assumed it's associative. SRS is RSR. R squared is equal to the identity. And we just found out that S times RSR is RS, and so on. And so we're getting a 6-element group. And it's not associative. RS is not equal to SR, for example. There's no reason for it to be. But now we're in a position to compare with S3. Now, I like to draw a picture of S3, the identity element, an element that interchanges the first two, an element that interchanges the second two. The product of those two in this order would be product of those two in the other order. That I did this with this one. The product of those two in the other order would be this one. And then the product of this one, and then this one would be RSR, like that. And now, if you think about what these are as permutations, this is the identity. And this is 1 and 2 are interchanged. This is 2 and 3 are interchanged. This is 1 goes to 3, 2 goes to 1, 3 goes to 1, and so on. And these are all 6 permutations. And you can see that, in fact, these multiply exactly like these. If I define this to be R, this to be S, then this is RS by definition, this is SR by definition, this is RSR. And it's certainly the case that R squared is equal to S squared is equal to the identity. And what about some other relations? Like RS times SR should be equal to the identity, right? RS times SR. But that's certainly true. If you put this down this way, you have RS, and then you're going to do SR, and RS. I wrote RS. That's interesting, but I wanted to do RS, SR. Right? That's RS, SR. This cancels in the middle because S squared is equal to the identity. And then over here, these cancel and we get the identity and so on. So you see that this is an isomer. But this group is not a group defined by generators and relations. This is just a group defined by mappings of 3 things to 3 things, which I'm drawing diagrams for. This is just the F of it is over here. F of this is over here, right? It's just a diagram of the function. And so S3 subscript. Symmetric group on 3 letters, group of permutations of 3 things, is in fact correspondent to this. And we can map this to this, and we can map this back to that. They're isomorphic. So now we know something interesting, though, in relation to our Trephone knot group, because our Trephone knot group is equal to the group generated by A and B. such that ABA equals BAB, which is some but not all of the relations for the symmetric group on three letters. That means we can define a homomorphism F from G to H by taking F of A to be equal to R and F of B to be equal to S. Homomorphism. And it's surjective. It's onto. And this group is not abelian. Commutative. And we know it's not commutative, and we know exactly what it is because it's a symmetric group on three letters. And that's definitely not abelian. There's no question about it. It could happen that you have something that looks non-abelian when you write it as generators and relations, but it collapses and becomes abelian. It could very well happen. But this guy is definitely this non-abelian group. And so you can't surject an abelian group onto a non-abelian group. No way that could happen, right? Because then this would have to be abelian. It'd be a quotient of an abelian group. So so that tells you that G is definitely non-abelian. So that implies that G is non-abelian and non-trivial. And that implies that the trefoil knot is knotted, even if you never knew anything else other than the group theory. And of course, the group theory is what happened historically first. So this is probably a rendition of the very first proof that the trefoil knot was knotted by Max Dane around 1900. That's the way it would have been seen, by using Poincaré's idea of the fundamental group and investigating by generators and relations the fundamental group of the complement of the trefoil, and then representing it, in this case, to the symmetric group on three letters, and you see that. This group is something like the symmetric group on three letters, except that it doesn't have the square of A or B equal to 1. And in fact, A and B have infinite order in there, but that's going to require that's harder to prove. And that A and B have infinite order. So that's a little picture of what the group theory looks like. And it's always like that in the sense that you could write down the group of a knot, and then you could wonder what kind of representations does it have? What could I find out about it? And that's very hard in general. It's not obvious how to get good concrete information out of something as abstract as a presentation of the group. But as long as we're, well, questions? Do you have questions about this? I want to tell you one more bit of lore about that group. So we have the fundamental group of the complement of the trefoil knot, which we call group of T, is given by generators and relations. Now here's a surprise. This is isomorphic to B3 equal to the 3-strand braid group. Now, I haven't talked about braid group yet, but I'll talk about it now for a moment informally. Braid group is a very nice idea. Braid group, due to the algebraist Daniel Larkin. I think in the 1930s, we can look up when he wrote his paper. I could even put in our in our collection, I could put a copy of his original paper about the braid group. But the idea of the braid group is that you put a group structure on braids. So braids are like tangles, but they can have many more ends. If you're dealing with a 3-strand braid group, you can think of making all the braids you want by using these 2 basic braids, sigma 1 and sigma 2. So for example, if you take a braiding pattern like this, then I would call this, first you did sigma 1, then you did sigma 2 inverse, then you did sigma 1, then you did sigma 2 inverse, and then you did sigma 1. That. Right? So in other words, if I have a braid, I haven't defined braid, you'll notice, but I will. If you have a braid and you have another braid, then you multiply them by sticking them together like this. Right. Okay, so that's the whole idea. A braid is a tangle box with strands that are unknotted and always descending from top to bottom of the box. You don't have any turnaround in the box, and they can weave back and forth across one another. 2 braids are equivalent if you can topologically move one to the other by Redmeister moves and keep the endpoints fixed, just like tangles, same thing. Okay, so that's all there is to it. But you can multiply them, if you will notice that there are inverses. For example, if you take sigma 2 and you multiply it by what I called sigma 2 inverse, so here is sigma 2 inverse, then this is isotopic as a tangle to the identity. And of course, sigma 1 inverse similarly. And if you have any braid at all, then you can make an inverse to the braid by basically taking a mirror image of it in the opposite order going on. So I leave it to you to think about how you would make the inverse, but the inverse is made just the way you would normally make it in a group. If you can factor something into a bunch of products, then you can, into a product of things, then the reverse product of their inverses will be the inverse. So if I have the braid here, sigma 1, sigma 2 inverse, sigma 1, sigma 2 inverse, sigma 1, that's my braid, and the inverse to that braid is going to be equal to sigma 1 inverse, sigma 2, sigma 1 inverse, sigma 2, sigma 1 inverse, right? Because when I multiply those two, they cancel out, and you have inverses for these. What I'm using to I hope, incite your intuition is that it should be more or less clear that any braid that you draw could be factored into little pieces that have only one bit of braiding in them. That's a lemma, of course, because you imagine some weaving. But if you have a weaving of lines where they're all separate from one another, I mean they're all going downward, and each one is unknotted, then you can kind of just tone them apart a little bit so that at any level, all you see are some vertical strands and maybe one pair crossing each other like that. Okay, so I'm not going into all the details, but it does form a group in that way. So that's the braid group. And if you look at the basic generator situation for the braid group, you find out that it is the third Reidemeister move for the third strand, 3-strand braid group. Look at that. If we do sigma 1, sigma 2, and then do sigma 1, and we compare that with sigma 2, sigma 1, and then sigma 2, sigma 1, sigma 2, sigma 1, versus sigma 2, sigma 1, sigma 2, they're equivalent, topologically equivalent. It's just the third Rademacher. Just take this guy and slide him upward. Right? So that's a relation in the braid group. And it turns out that the three-strand braid group is given by exactly that relation. It's the same as sigma 1 and sigma 2, which is sigma 1, sigma 2, sigma 1 is equal to sigma 2, sigma 1, sigma 2. There are no other relations in the three-strand braid group. And so the three-strand braid group and the trefoil knot complement have the same group. That's a nice coincidence. And you might wonder, well, what's going on there? There must be something behind that. Well, there is, but I'm not going to talk about it right now. It is related to the fact that, well, I didn't want to tell the story. There is a story. Maybe you could find another story. So now what about more strands? That's the natural question to ask. Suppose you had the four-strand braid group. Well, then you would have the four-strand identity, and you would have a sigma 1, and you would have a sigma 2, and you would also have a sigma 3. And those are weavings between adjacent strands, so your intuition should suggest to you that any weaving at all that I make with four-strand braid could be combed a little bit so that at every level I would have just one of either sigma 1, sigma 2, or sigma 3. Try it out with some pictures yourself and see if you can prove it. But now we have another relation, because look at what happens with sigma 1 times sigma 3. They don't have anything to do with one another, and this is exactly the same as doing it in the other order. So sigma 1, sigma 3 is equal to sigma 3, sigma 1. So there is another kind of relation that can happen in the braid group. Namely, if they're more than one step apart, they commute with one another. And it turns out that the n-strand braid group is going to be given by sigma 1, sigma 2, out to sigma n minus 1. Just like 4 to 3, right? First 2, second 2, third 2, last 2, and the last 2 is n minus 1 weaving with n. So n minus 1 generators, and sigma I plus 1, sigma I is equal to sigma I plus 1, sigma I plus 1, wherever that makes sense. And sigma I, sigma j is equal to sigma j, sigma I, when the absolute value of I minus j is greater than 1 when they're farther apart. Okay, so that's a theorem. That the n-strand braid group, which is defined geometrically, as I said, tangles, strands always going down. No strand has any knots in it. Take the tangles up to tangle equivalence. Then as a group, it's given by this. And this, as you see, is a generalization of the symmetric group. Well, do you see? It is a generalization of the symmetric group, just like we had before, because if you were to consider elements in the symmetric group, permutations, say, of 4 things, then you would have 4 dots here, 4 dots here, and you want to permute. So maybe you take this to this, take this to this, take this to this, and you leave this alone. And you draw a diagram like that, but that can be factored into crossings between adjacent things, just like I was doing with the braids. That is to say, a fact about permutations is that any permutation can be factored into transpositions. A transposition being a switch between two adjacent numbers. And that's the picture of combing the braid. It's a braid, but it's a flat braid. Any permutation is a flat kind of braid. But then if you define the generators there, you would have T1, T2, and so on, where those are the transpositions. And you will find that Ti plus 1, I'm talking about the symmetric group on n letters now. Ti plus 1 Ti is equal to Ti plus 1 Ti plus 1. It's the same diagram as the third Yang-Baxter move. The underlying permutation here is the same. That's the point I'm making. That if you think of this, 1 goes to 3, 2 goes to 2, 3 goes to 1, still true over here. Underlying permutation goes the same way as before. So what you have then is that the symmetric group, I'm going to do work by erasure. You have that the symmetric group on n letters is given by transposition T1 through Tn minus 1. And Ti squared is equal to 1 for all I. And Ti plus 1 Ti is equal to Ti plus 1 Ti plus 1 and Ti and Tj commute. And I and j are more than 1 apart. And the picture for that is drawing permutations the way we were drawing them before. And then you'll see that if you have a triple of them right next to one another, then they do something that looks like a flattened Yang-Baxter 3 move. If they're farther apart, they commute. And of course, they square to the identity because they're just interchanges. So the symmetric group and the braid group are related just the way we were doing it for the Treffelman group. And there is a homomorphism from braid group to the symmetric group, F of sigma I equals Ti. You just look at the underlying permutation related to the braid, and you're going to map to the symmetric group. This tells you that the braid group is very non-commutative and very non-trivial. It doesn't tell you that the individual sigma i's have infinite order, but I brought it all up partly because I wanted to point out that your intuition can now show you why they're of infinite order, because if I, for example, were to write sigma 1 cubed, here's my picture of sigma 1 cubed, and there just is no reason for sigma 1 cubed to be trivial in the braid group, right? It's twisting around itself. Some linking number arguments will get you even numbered ones or non-trivial, for example. So the braid group is a group structure on the diagrams of things, and it's very fundamental to lots of things in topology. partly because it's related to the symmetric group, and partly because there's a beautiful theorem due to Alexander that says that every knot can be written in terms of a braid. I'll show you in a moment. But do you have any questions about this? I've been sort of nattering around and not being too systematic here, but I did want you to see the braid group articulated. Okay, so Alexander's theorem is the following. Suppose you have a braid. Then I can form the closure of the braid. There's more than one way to close a braid. This is the standard braid closure. I often think of it. This is one of this braid closure. So Alexander proved Alexander's theorem. Every knot or link is the closure this topic by Braided, the closure of the braid. Here's a knot on this already. Maybe this is too complicated knot. Okay, maybe it's too complicated, but I want to illustrate Alexander's method. So you have something and it doesn't at all look like the closure of a braid. What does the closure of a braid look like? Let's draw one so we see it. I might take this four-stranded braid here and close it. So there's the closure of a braid, and I think I have a knot here. Yeah. So this is the closure of a braid, and there's a knot presented as a closure of a braid. So if you have a knot presented as a closure of a braid, then it means that you can put the knot in such a way that it's always circulating around a center point or around an axis, right? That's really what we're saying when we say that the knot is the closure of a braid. And we're saying that it's given in a form that circulates always in the same direction around some axis. So was Alexander's idea. He said, well, here you take your knot and you choose an axis. And now you hope that you chose an axis for which it's circulating around the axis. But it might not be. Like here, if you're looking at this thing that I just did, I could go around for a while and I'm circulating around, but then I get to here and this one isn't circulating around the axis, it was going backward around, the other way around, and I would like it to be circulating around the axis this way. So I pick this up and I put it around the axis. And lo and behold, it's now completely circulating around this axis. And I'm done. So Alexander said to himself, I'm reconstructing. He said to himself, well, that's good. Maybe I could always do this. Maybe I could start by just choosing an arbitrary axis, and then I walk around the knot, and whenever it's going in the wrong direction, I pick it up and I put it over the axis so it's still circulating around the axis. And then I'll keep on going and go all the way around the knot until I come back to where I started, and it ought to be circulating around the axis all the time then. And he was right. And if you try that out, you will find that you are holding a proof of Alexander's theorem in your hand. try it out either by drawing or taking some rope like this and see that what I've told you is true and that it really does work. That all you have to do is walk around the knot and correct it with regard to the axis at every point when it goes wrong. And by the time you come back to where you started, it will be circulating around the axis and you will have turned the knot into a braid. One of the best proofs I know belongs in the book, Erdős's book that God has of all the best proofs, right? You know that book, or you'd like to know that book. Okay, so that's Alexander's theorem. Every knot is the closure of a braid. And then there's another theorem, which came a little later, which is Markov's theorem. Markov theorem. Markov theorem tells when B bar equals B prime bar, when B and B prime are equivalent as knots, when B and B prime are two braids. Now that would be good to know, wouldn't it? Because then you could do a theory of knots based on braids. You would say, I only study braids, and I have a certain method of telling when two braids will give me the same knot. Would be good to know. And in fact, it is a nice theorem. And the theorem goes as follows. There are two moves. Two basic Markov moves. One of them is that you take your braid. I'm using 3 strands, but of course it could be any number, and you conjugate it. Take another braid up here, alpha. You put the inverse of that braid down here. So you take B and you replace it by alpha B, alpha inverse, where alpha is some braid, and they have inverses, you can conjugate by them. That's a different braid. For example, if we started with the braid that gave us that knot, that was the figure 8 knot, by the way, the knot that we had. This braid closed to give us the figure 8 knot on the previous board. The four crossing knot that I got on the previous board was equivalent to the figure 8 knot. But then up here, I could decide that I think I like to conjugate by sigma 2. Okay. And then I have to conjugate by sigma 2 inverse here, which would be this. Now, in this case, there was a sigma 2 on the bottom and these canceled. Well, this is now B prime. B prime is equal to sigma 2, B sigma 2 inverse. But then it actually simplified a little bit and turned into this one. I'm wasting your time by bothering you with this. 1, 2, 3, 4. Yeah, okay. Because these two cancel, that's all I'm saying. But this is B prime, and it's a different one than B. B being what goes between here and here. That was B. Sigma inverse. Sigma inverse. There, like that. So you could do that. Now, why am I bothering you with this move? Oh, because it's obvious, isn't it, that if you close it, then you get the following. You get B, get alpha up here, get alpha down here, inverse. And alpha and alpha inverse are allowed to communicate with one another. But they kill each other off, alpha times alpha inverse. Once they communicate, they just undo one another. And so this is the same as the closure of B. So that's one way in which you could have two different braids that have the same closure. Here's another. You're sitting here with a braid, and you add an extra strand going up to the next braid group, and you put a crossing here. This is, we'll call this B tilde, all right? So that's called the stabilizing move, Markov stabilizing move. But you see what will happen if you close B tilde. Then it will all go away at this. And then you decided, I'll close it. And this is exactly the same as B closure because there's just a third Reiner-Meister move loop in there and you remove it. So a third Reiner-Meister move loop is lurking here, but it's a different braid. It really is a different braid. So, so this is Markov stabilization. So the moves are conjugation, stabilization. And the theorem is, Markov theorem is, that if you have two braids that close to the same knot or link, then you can get from one braid to the other by doing a series of conjugations, which keep you in the same braid group, or Markov stabilizations, which can drop you into a lower braid group or put you into a higher braid group by means of either adding this kind of thing or removing it. And that requires some work to prove that, more work than we had to do to get the Alexander theorem. The best proof I know of this theorem, the best proofs I know of this theorem came after the proof by Markov. And it has an interesting history. Markov proved it, but never wrote down the proof, except in some notes maybe. And then Joan Berman in the early 1970s, wrote her book on braids, links, and knots. And that's an Annals, Princeton Annals book, a very good book. And she gave a very detailed proof of the Markov theorem in her book. That was the first time it appeared in print. And then later, Pierre Vogel gave a simpler proof, and Sophia Lamberpoulou gave a proof that is very useful because it can be generalized in a lot of different directions. And I think that Sophia, when the conference starts in 2 weeks, will be talking about Markov theorems and braids, so you may get a chance to hear about that a little later. The Markov, but you see, this is a very nice and important reformulation of knot theory that says that instead of just doing knot theory on arbitrary knot and link diagrams, you can do them on braids, but you have to respect the Markov theorem. And it took a long time for people to realize that they could really do that. That is, you can write down some ways of getting invariance of knots and links by writing invariance of braids that will be manufactured to be invariant under conjugation and invariant under the Markov stabilization move. And if you could do that, why then you would have new invariants of knots and links. And we'll come to that. But I did want to talk to you about that a little bit. So that's a picture of the Markov theorem. Questions on that? Okay. more loose ends, simpler loose ends. I said to you a while back that it would be good if you could understand why it is that you can always checkerboard color a diagram. Did anybody try to prove it? Checkerboard color means that I'm going to color the regions in black and white, so that if two regions are adjacent to one another, they have opposite colors. And then we went on the other day and said, well, out of that, if you want to, you could make a graph by putting a vertex in every one of these regions and connecting them by edges if they shared a crossing, and you get a graph associated with an outer link. But how do you know that you can always do this, that it will always checkerboard color? We'd like a proof of that. There are many proofs. One proof that I like is the following. I say I'm going to convert this knot diagram into a Jordan curve. Let me do the conversion by starting with the diagram itself. I got the same diagram there. I want to convert it into a Jordan curve. So what I'm going to do is I'm going to smooth the crossings in a certain way. So let me make an unknown diagram out of it for a moment. Now I claim that that's going to be hard to see. It's going to be hard to see. Let's do it differently. Let me start with this one. If I had this and I was going to smooth the crossings, if it was checkerboard colored, then I would have a very nice choice of smoothing a crossing. Smoothing a crossing means to rewrite it so that it's not crossing by reconnecting the lines. I can smooth it that way, or I can smooth it the other way. Okay, there's two ways to smooth a crossing. So I want to smooth the crossings on this so that the black regions are communicating with one another. And that's easy once I have the black region. Somebody and I could do that. For this problem, my life is easier than I thought. I have some knot diagram. Let's choose a different one. And I decide that I'm just going to eliminate all the crossings. Then I'm going to put in for them smoothings in some completely arbitrary way. I don't care how I do it. I could try to keep it connected if I wanted to. I was going to worry you about keeping it connected, but I don't have to. But what I get after I've done that is a collection of simple closed curves in the plane, right? And every simple closed curve in the plane, every simple closed curve in R2 provides R2 into a connected inside and a connected outside. This is called the Jordan curve theorem. Right? And of course, it can happen in a rather complicated way, right? But we're only dealing with curves with finite numbers of complexities in them. They don't wiggle on, they aren't fractals. So I don't have all the worries I might have about this theorem. I'm just talking about very simple curves that are differentiable. And I will get some Jordan curves if I take an arbitrary link diagram and do some smoothings on it. But now, given that, I can start in the following way. Label the outermost unbounded region white for the Jordan curves. If I cross a boundary, I'm inside that Jordan curve, and I call it black, and that colors that one black, and I'm still white on the outside here. And if I crossed another boundary, it would be black. And you will get a black-white coloring of the Jordan curves in the plane. If you have a bunch of disjoint Jordan curves in the plane, just follows from the Jordan curve theorem. I'm either inside or outside a given curve. They can be nested in some complicated arrangement. I might have a curve within a curve, and a curve next to a curve, and another curve around that. And I go white, black, white, black, white, black. And now I have colored every region in this plane in such a way that if two regions are next to one another, they're colored differently by using the Jordan curve theorem. Clear? But now all we have to do is put the crossings back in, because we're going to be in a situation like this. White, black, black, right? Something like that. That's the way it's going to look at every one of these places where a crossing was removed. And if you put the crossing back in, you don't disturb these at all. All you do is make sure that you have that designator white on both sides of where you close the crossing. And it will still be colored in such a way that the graph that you made is colored with two colors, so that if two edges are adjacent to one another, they're colored differently. So that's my proof that you can always do color and not diagram. It follows from the Jordan curve theorem. Okay? Now, you might think, I'd like a different proof. Well, see if you can find one, because there are many proofs of this. Now comes another theorem. Every diagram, let's say knot diagram to make it easier. Every knot diagram, it doesn't make it easier. Every knot or link diagram can be made alternating. Slow down. Alternating. By choosing the crossing. I don't say that you can isotope it through an alternating diagram. You cannot. But if you're allowed to choose the crossings, you can make it alternate. So for example, I take this diagram here. And I wish to make it alternating. So I just do so. And I claim it always works. So I say, okay, over. Next one has to be under. Next one has to be over. Next one is under. Next one is over. Under, over, under, over, under, over. Done. Alternating. The claim is this always works. Another construction that you can always do, and I think we mentioned it the other time, but I didn't do it. You can start and draw over before you go under. Oh, we did. It's worth mentioning. You can always draw it so that this is over before under. This is alternating. Okay. Now over before under, of course you can do that, and it's unknotted, and we've mentioned that before, but it's worth talking about in the same breath because these are general structures that can always be put on any diagram. Alternating is about as knotted as you can make something, and over before under is very unknotted. What other loose ends do we have? One more that I can think of, and you probably can think of a few. No, I can think of more than that, but I was showing you the Wang algorithm for calculating, for enumerating the trees in a graph. And I said that in the Wang algorithm, you would work in the odd two coefficients of labels in the ring of labels in the diagram, A, B, C, D in this case, such that each label at square is 0. They all have square 0. You work in that ring and you do a certain thing. And the thing that I said that you should do is to choose all but one. So I'm going to, this wouldn't be the one I don't choose. And I'm going to take A plus B plus C multiplied by C plus D multiplied by B plus D. And then the claim is that if you multiply all that out and reduce it in this ring, you get a list of the trees. And with this version of the example, you can see why it is that I'm working Z2. Because when you multiply this out, you can get a cycle as a product. You could get C from this, D from this, and B from that. But you can also get B from this. You could get C. You can think of this vertex as choosing C, right? Because this is this vertex, 1, 2, and 3. And you have 1 and 2, and 3. So you can think 1 chooses C, 2 chooses D, 3 chooses B, and you get CDB. But you could also think 1 chooses B, 3 chooses D, and 2 chooses C, and you would also get BCD. You don't want it to occur at all, but it occurs twice. And in this algorithm, cycles will produce, if there is a cycle, it'll end up having been produced twice. And that's the Z2. That's why you need the Z2. I wanted to mention that. So if you multiply this out, you see what will happen. You get AC plus AD plus BC plus BD plus C squared, which is 0, plus CD times B plus B. And then you get ACD plus ABD plus 0 plus 0 plus CBD. And then multiplied by D, I get ACD plus 0 plus BCD plus 0 plus 0. And I should find BCD twice. CBD, there it is once, and CBD, there it is again. And that's a case of cancellation because it's C2, and I end up with ABC plus ABD plus ACD. ABC is that tree, ABD is this tree, and ACD is that tree. It works. Okay. So if you're enjoying that, trying that out, that's the reason why I needed over C2. Okay. Here's another example that you can try. If you take the figure 8 knot, let me write out part of this. We're getting back to Alexander polynomial. If we wanted the Alexander polynomial with the figure 8 knot, according to the method that I was just showing you last time, then you would write out the Alexander's quandle, what I call Alexander's quandle. So here's the knot, and I claim that well, you can write down. I'll write them down. That A is equal to D sharp B. You get D is equal to C star A. That C is equal to B sharp D. And you get B is equal to A star C. Right? And notation. I often write star bar, the one that's the opposite of the star, instead of sharp. And I think I prefer it. But this is just writing down the relation, right? A is equal to B star D star B and so on. And then you can continue on substituting in there and find that the basic relation is this one. B star bar D star B star bar B. By substituting and getting rid of variables, keeping D and B. So this is an exercise. You could get to there. You would. And once you've gotten to there, you can then write D is equal to T times B star bar D plus 1 minus T times B star bar B, because that's what the A star B is equal to TA plus 1 minus TB, remember? So you start writing this out and you keep on going, writing it out, and you will find that in the end you will arrive at 0 is equal to T squared minus 3T plus 1 times B minus D. And that tells you that the Alexander polynomial of the figure 8 knot is equal to T squared minus 3T plus 1. And you will note that the Alexander polynomial evaluated at -1 here is 5. Which you expected because you knew that the coloring number was 5. So that's without the details, what happens with the figure 8 knot. And figure 8 knot is a very interesting knot for many reasons. So this is a good exercise for you to sit down for half an hour and fill in the details and actually see that it does work out that way. Okay, so we have 3 more lectures, and so I'm not going to go into other aspects of the Alexander polynomial, although I would like to. But I'm going to go over now to the bracket polynomial. and the Jones moment. And these invariants use nothing but diagrams. They don't have algebra structure to talk about. They're simpler, but they're also a little more abstract. So I just want to introduce you to this idea, and then we'll see how it works next time. So I'm going to define an invariant, which I call bracket K, and this is going to be invariant under Rademeister 2 and Rademeister 3. And we'll normalize it to get it to be invariant under Rademeister 1, but it's most convenient to not worry about making it invariant under 1 until later. And it's going to satisfy a recursion. This. And like this. You had a diagram, you had an extra loop that will multiply by a value for the extra. And we're going to find, we will find, that D equal to A inverse and D equal to minus A squared minus A to the minus 2 will make bracket invariant under Rademeister 2 and Rademeister 3. And it's as simple as that you can take a diagram. So let's do an example to see what I mean by this. Take a diagram like this. And if I wanted to compute the bracket of this diagram, then I choose a crossing and I expand it according to this rule. So I would get A times the bracket of this plus B times the bracket of this. Where what I have done is I have taken this guy here and I have moved it this way, or I just moved it that way. Okay? And those have one fewer crossing. And I can do this again. I can work out each of these, but maybe those will come up a lot, so we might as well work them out separately. I'll just do this and we'll stop for today. So if I worked a little curl and saw what it would do, it will do this. It'll multiply by A and leave me with a loop, and it'll multiply by B and come together, and then I will get AD, because if there's an extra loop, you multiply by that and B, and then it will be out, okay? And if you had it the other way, then you will find that you get A plus BD. So that's what happens under those, and then you see that what will happen here is that we're going to get A times, what is it going to be? Which one is it? How do you tell the difference between these two? Well, if you were to orient the curl, then you see that the one that got A D plus B is the positive curl, and the other is the negative curl. That guy's a positive curl. Let's put a little orienter on it. And so you get AD plus B here, value of loop, plus B times the other one. And what is this one? This one's a negative one, so that's A plus BD times value of loop. And if we take the value of the loop for simplicity to just be D, we'll normalize that later too. Then we have A times AD plus B times D plus B times A plus BD times D. And I have translated the link diagram into a polynomial in A, B, and D. And if you think about this a bit, we have to do those thoughts next time. You see that this is independent of the order in which you did it. So you get a well-defined polynomial in 3 variables assigned to every link diagram that you put down. If you move the diagram around, of course, it will change under Reidemeister. But here we have material for thinking about getting a link invariant. We have a method of assigning a polynomial to the link diagram. And what we have to investigate is how will it behave under Reidemeister moves? And we will find that if we specialize the variables in this way, then that polynomial will actually not change under Reidemeister moves 2 and 3, and we have an invariant. So this is working purely combinatorially, no group theory, no quandle, no quotienting by a lot of equivalence relation, just ordinary algebra. It turns out that we get a lot out of this. Enough so that it will occupy us for the rest of the course, because I'm going to tell you about what you can do with this next time, and then we'll spend the last 2 days talking about a generalization of this that's called covariant homology. So that's a plan for the rest of the time.